So it's a great pleasure to introduce Lianne Sheppard, a very long-term colleague of quite a few of us. She's from the University of Washington Biostat Department with a long history of involvement in environmental epidemiology projects. She's been a key player on the Clean Air Scientific Advisory Committee for EPA and a variety of other regulatory studies and so on. So without further ado, let me just let her just go ahead and talk to us about her experiences. Lianne, it's all yours.
Okay, thank you. So sharing my screen and you see my slides, right?
We do.
Okay, great. So what I wanted to talk to you about today, I've actually gotten pretty interested in design and exposure assessment because the Achilles heel of all environmental epidemiology, in my opinion, is the exposure assessment. And also quite interested in mobile monitoring studies for traffic-related air pollution. And so I'll talk to you about that today. If I can figure out how to advance my slide. There we go. So I'll give you some background and context about why we're focusing on this, and then focus on this work we did on study design, actually using a simulation study with California data, and then our Seattle study that we conducted in 2019 and finished right before the pandemic hit, which was convenient. So I think most of you in this audience probably know some of this background, that evidence has linked traffic-related air pollution to neurotoxicity, including late life dementia incidents and reduced cognitive performance. And this paper, Power et al., is a nice review paper that covers the landscape in terms of those relationships. And again, many of you probably know traffic-related air pollution is a complex mixture of gases and particles. And I'm particularly interested in ultrafine particles, or PM.1. And this figure, the classic figure showing you here, and PM10 and PM2.5, and now ultrafines even smaller on there. In terms of brain health, there's two main pathways that are believed to be important in terms of brain. There's the direct and the indirect pathway. And PM.1, or ultrafines in blue, actually is important for both the direct pathway directly in through the olfactory bulb into the brain, as well as indirect entering the circulatory system, as likely PM2.5 and perhaps PM10 do as well. And so there's a belief that these smaller particles may induce more damage and inflammation. But most of the evidence about ultrafines is not from humans, and if it is, it's short-term studies and animal studies, and we're really interested in long-term effects with cohorts. So again, as many of you probably already know, the traditional TRAP exposure is based on the regulatory monitoring network. It's long-term and spatially sparse, and they don't have all the pollutants we want. A lot of studies add their own monitoring networks, which are spatially denser, but also short-term. But an emerging approach is mobile monitoring, where you pretty much drive around and collect data from a car. So you collect, the idea behind it is you collect repeat short-term samples and use those to estimate long-term averages. And so that's time and cost efficient because you can sample pretty short times at any individual location and cover a lot of ground by driving. Just use one platform so you can afford a lot of high quality instruments. One of the challenges with existing mobile monitoring studies is they use convenience sampling. So they're really short time periods, like a couple of weeks, and they may just focus on the business week, so Monday through Friday. They may focus on non-residential areas where people in our cohort don't live. And they may also rely mostly on on-road or so-called mobile samples versus stopping and parking. And the pictures on the right just give you an idea of the inlet and the instruments, and again, our vehicle. So all of this is motivated by a study that we're doing, which relies on the adult changes in thought study. And while I'm not going to talk about any epi results, I think it's context for what we're doing. And it's been a long-term study, started since 1994, looking at aging and the brain, and they have over 5,000 participants. They're still recruiting a few people a year as people drop out, and they're all elderly, 65 plus, and dementia free at baseline, and they get cognitive assessments every 2 years, and then they stop following once they get diagnosed with dementia. And so we have the ACTS in adult changes in thought air pollution study, which leverages that study along with pretty state-of-the-art exposure assessment to look at cognitive decline and dementia incidence, as well as changes in the brain. And actually, there's a whole nother research topic, if you all are interested in that. My colleague, Marco Carone, is leading some of the work we're doing and thinking about causal inference with autopsy samples. And it's actually a pretty elusive problem. But today I'm going to talk about mobile monitoring and first design and then our study. And so there's actually no literature on how to design a mobile monitoring study. So what we did was use existing data to learn about how design influences annual average exposure predictions, because that's what we want to use in our epi cohort studies. And so what we did overall was to simulate realistic mobile monitoring campaigns with existing regulatory monitoring data. And we were particularly worried about a couple of features in our 2019 study. So we really focused to some degree on that. Our study was balanced on time of day, day of week, and season of year, but we didn't get all hours of the day in all sites the way we wanted. So we wanted to understand that better. And we also wanted, for perspective, to look at some common designs in the literature. Those are typically restricted to 2 seasons and often rush hours or business hours. And then because we could in a simulation study, we wanted to also compare short-term sampling, which is what you would do if you were doing a mobile campaign, and long-term sampling where for whatever design, it's as though you put the instrument there the entire time period. And that gave us some interesting perspective. So the data we used actually from your state, California, 2016 hourly NOx data. And we had some inclusion criteria, make sure we had enough data at the site, and we didn't want rural or industrial sites. And we ended up with 69 sites, and over here just shows you where the sites are in the state and the levels of NOx in 2016. So I'm going to go into, I have a table on the next slide. It's a little complicated, so I wanted to help you think about the sampling framework we used first. So we thought about 3 different designs, generally a balanced one, and then the 2 common, the rush hours and the business hours. And then we had 2 different sampling approaches, which I already introduced, short term, which is like mobile monitoring, and long term, which is if you had the instruments, you would leave them there according to the constraints of the design. And then we looked at several different versions for each design so that we could look at different kinds of restrictions or different seasons. And then within each of those, what we're calling a campaign is as though you did an individual study. And so for a short-term campaign, we had only 28 hours sampled per site, as though you drive around and come back 28 times. Whereas the long-term version, we had all the possible hours. And that's not a realistic version, but it was useful to look at. So this is a complicated table, and that's why I wanted to introduce it. We have the 3 kinds of designs: the balanced design, which is year-round, the rush hours design, which is 2 seasons during the weekdays and only during rush hour, and then the business hours, which is also 2 seasons only during weekdays. And then, for instance, and this is actually our gold standard, the year-round balanced long-term. And so we basically, it's all the data we had, at least for version 1, the gold standard, and that was a maximum of almost 9,000 hours. The most hours was restricted because nobody really wants to drive a car between midnight and 5 a.m. So we wanted to look at that, and that was one of the restrictions we had in our campaign. And then truncated hours, there were a few sites that actually in practice were really only visited 3 times a day. So we wanted to look at that as well, and that's the version 3 truncated hours campaign. And so again, as I mentioned, the short-term version is where we have 7 samples per season, 5 during the week, 2 on the weekend, and then random hours according to the time of day we were sampling. And so we got a total of 28 measurements, and we looked at, because of the variability in that, we looked at 30 campaigns for each of the short-term designs. And then similarly for rush hours and business hours, we have 2 types of versions. Version 4 and 5, we look at winter and summer as our 2 seasons and different 2-week periods. And version 6 and 7, we look at spring and fall. And similarly for the business hours, they're both restricted to the week. Rush hours is restricted to the times of day, which are typically rush hour, and business hours are the typical business hours. And then the long term, took all of those hours, and the short term took just 28 of those hours. So in brief, what we did is we created the campaigns by doing the sampling according to the plan I just described. We compute the annual averages. We get prediction models using log NOx as the outcome with partial least squares that we derive from 180 geocovariates, as though that was the data, as though we had a campaign. So we did it sort of separately for each campaign and looked at model performance with tenfold cross-validation. And here we use both what you would be the traditional approach, where you use the measurements, the observations from the campaign, the site averages. But we also, since we had it, we looked at our gold standard, which is all the measurements for the site over the entire year. And we also, I'm not going to talk about it today, but we also looked at NO2 and NO. So now the results. So first of all, the estimates, this is the single long-term campaign for the 3 balanced design version, and then the 3 rush hour design and business hours. And remember, the colors, their winter, summer are the first 2, and spring and fall are the second 2. And this is only one of the 30 short-term campaigns. So obviously a little bit noisier because they're only 28 hours. But the important takeaway message of this is what matters is not the long-term versus short-term, but the design in terms of the differences in the distributions of annual averages across sites for the various designs and versions. If you look at the site level, and this is a figure that is a sample by high, middle, and low concentration. So below the 25th percentile, in between the 25th and the 75th, and above the 75th percentile, based on the true annual average. And then the box plots are the 30 different campaigns. And you see the balance, the 3 versions, rush hour 4 versions, and the similar 4 for the business hours. And what you see is there's not that much bias, and these are all relative to the gold standard. You don't see much bias across the campaigns and across sites for the balanced designs, but you see some interesting patterns that vary by site for both the rush hour and the business hours, where the business hours tends to underestimate more than the rush hour, and the rush hour is more likely to overestimate, but they also depend on the sites. If we look at the predictions, and these are the cross-validated predictions and compared to the gold standard prediction, and these are actually the data for the different campaigns by colors, which are given down here. And these are the fitted relationship between the prediction for each campaign and the gold standard, where we have a thick line that's an overall trend for each campaign, and then individual, it's sometimes hard to see, but here you can see individual variation across campaigns. And you see that the most accurate predictions were for the balanced designs, and there was generally a positive trend for rush hour and generally a negative trend for business hours, but it varies a little bit based on whatever version, whatever set of 4 weeks we happen to sample. And then here are the prediction biases, the same idea compared to the gold standard predictions. And so same plot as I showed you for the estimates. And overall, we get pretty similar patterns for them, although there are a couple of exceptions. If you go back and forth between them, there's a few differences, particularly these high sites, between the estimates and the predictions. Now, what I think as a statistician, this is probably the most interesting part of the work we did. So this is model assessment. And first I'm showing you model assessment versus the true annual average. So since it's a simulation, we know the truth. And the little square boxes are the long-term average. So this is the prediction for the gold standard here, because it's the all hours design, and then the various truncated designs for the balance, and then for the and I forgot to mention, so we have the R squared, the mean square error, which accounts for both bias and precision, whereas this is the regression based R squared, or the square of the correlation. So it's adjusted for the bias, because it's around the best fit line. And here's the root mean square error. So each box is for the 30 different campaigns, and then the little square box inside is the long-term version. And you see overall, as we would expect, that the balanced all hours design does the best, and you get a little bit of degradation when you don't sample all hours of the day, and a little bit more variability across campaign. And the other designs don't do as well in terms of root mean square error or R squared, although that a lot of this is bias, and it's not as obvious when you do it around the best fit line. The other thing I want to point out is occasionally you get a campaign that's just not going to perform as well. Only 28 hours in a year, and so there are occasional campaigns that aren't as good. However, when you look at the comparison, and now the figure I was just focusing on is the left-hand column, oops. And the right-hand column is the campaign average. So it's the observations you would collect, and you get, and that's what we would typically do for traditional model assessment. And you get a fairly different impression from the campaign averages, where there are some campaigns, for instance, here, this business hour campaign is a good example, where you're actually doing better when you're comparing it against the observations than what you're seeing, than what you would be seeing if you compare it against the gold standard, which is up here. So because the observations themselves are biased, the model assessment we're doing is not really revealing what we want to know. So what we haven't been able to answer yet, but we look forward to thinking about more, is whether mobile monitoring study design actually, how it impacts the inference in an FE study. And I hypothesize that there is some differential exposure measurement error in these bias designs. And so that's something I think we need to try to elucidate. So now I'm going to switch gears. Let me look at the time. So, and I talk about our 2019 mobile monitoring campaign, which motivated the simulation work I just showed you. And so our goal was to characterize annual average traffic-related air pollution exposure in our cohort, and then ultimately, which we haven't done yet, look at the association with less commonly measured traffic-related air pollutants on brain health. So what we did is this is the greater Seattle area, and we identified 9 different regions, and within them we had 33 locations where we stopped. And all of these were representative of our target cohort, and also were set up to maximize spatial coverage for the cohort. And we had these fixed driving routes since we were going to be collecting data continuously. And we tried to drive not necessarily the closest route, but a route that would maximize driving in residential areas. And we had a pretty strict driving schedule to try to get balanced sampling. And this first slide shows you the same stops with the gray is the ACT participant locations. And then over here, the figure shows you the density of some of the key covariates, like distance to a major road and distance to the airport, railroad, population density, and elevation, and the density for ACT residents versus the selected park stops. And we intentionally tried to select the park stops so they were representative of the cohort, because we know in environmental epidemiology that spatial compatibility of the exposure monitoring locations with the cohort locations, and this is an important property for measurement error correction. So we wanted to target that. And we ended up with more, we were targeting 28 samples, but we ended up with more like 27 per site at 309 sites. And as I said, we ended right before the pandemic hit. And we tried to get all seasons, day of the week. We succeeded on both of those. The time of day was a little more challenging. We didn't sample between midnight and 5 a.m. And as I mentioned earlier, there were some sites that we really only visited 3 times a day. And we measured ultrafines, black carbon, PM2.5, carbon monoxide, CO2, and NO2. And so this just shows you the platform with the manifold and our driver with the laptop. And I don't know how many people here are instrument people, so, and I'm not so much, so I will leave this up and just make a couple of brief comments. And that is that we had 3 different ultrafine particle instruments, a nanoscan, a disc mini, and a P-track, with 2 P-tracks actually, one with a diffusion screen that was a 1 cut point in terms of size. We also measured black carbon with the micro F, and working with Tim Larson, those of you who know him, of course, we had to measure PM 2.5 with the nephelometer. And and we also had temperature, relative humidity, and of course the GPS, so we knew where we were. So I'm going to focus on ultrafine particles and black carbon. This is work that my recently graduated student Magali Blanco did for her dissertation. And so she focused on the P-track, the 1 unscreened P-track, and the black carbon from the micro F. And to get predicted exposures, we had to come up with annual averages. So, we had measurements at the 1 or 10-second time scale over our 2-minute visits at all these stops. So we took the median of the 1 or 10-second data, and we trimmed those because we are worried about these short visits having some extreme observations. So that was a 5% trim mean, and that's an interesting conversation to have. We instead of just calculating the average at the site in order to address the fact that we had some imbalance, we actually used a linear regression model to get the annual averages after we trimmed off the couple of observations, one on each end on average. And then we predicted using universal kriging with partial least squares and predicted at the cohort residences. And what we learned is in line with the literature that, higher predictors of traffic indicators, population density, land use development, ports and rail yards were all positively associated with both ultrafines and black carbon, whereas green spaces and vegetation were negatively associated. And here's the prediction surfaces. We predicted a little bit outside of the driving area at some of the edges, and you see in this, the left is for ultrafine particles and the right is for black carbon, and you see higher predicted concentrations, particularly between downtown Seattle, for those of you who know Seattle, and the airport down here. And this is an interesting thing I'm going to bring up at the end. And that there was a couple of differences that are even noticeable in just comparing these two maps between ultrafines and black carbon. For instance, ultrafines are higher at the airport and black carbon tends to be higher around the port and the rail yards. And one of the things that, black carbon, in general, there's more black carbon data than there is ultrafine particle data. So one of the things we looked at was whether you could just use black carbon as a surrogate for ultrafine. And so we looked at the relationship of those, both for our 309 sites and also for cohort predictions, to identify the kinds of locations where they're pretty different. Either the ultrafines are much higher or the black carbon is higher. And these maps on the left for the 309 location estimates, and on the right for actually grid predictions, not cohort predictions, show you, and all of the circles are from the scale, but the ones that have black circles around them are the residuals that are either that are on the extremes, either high or low. And you can see that in general, we have higher predictions around the airport for ultrafines and lower around rail yards and large ports. So using ultrafine particles as a surrogate, using a surrogate for ultrafine particles such as black carbon may produce some important exposure misclassification in terms of what we care about. Now, this is also quite interesting from our study. This is putting our predictions in context. The left-hand side is for ultrafine particles, and the right-hand side is for black carbon. And the estimates are the mean concentration for different studies. And there's 3 different types of studies. There's the fixed site continuous. So this is where monitors are put at a specific location for a long period of time. That's what we mean by fixed site continuous. Short-term mobile, what we mean is the vehicle, it was a mobile campaign where the vehicle didn't stop for any length at all. So it was purely mobile data. And short-term stationary is like what we did in our Seattle campaign, where we stopped for 2 minutes at each site. And what you see is we're much lower than pretty much all the rest of the studies in Seattle. And why, you could ask? Well, one is our air is probably much cleaner than many of the places. Also, we targeted different areas. We had a wider geographic area that we sampled and sampling time, so that could have affected our levels. And so our averages are more similar to people that sampled in rural and suburban locations. But what's particularly interesting from a design perspective is we actually had quite, even in spite of our lower averages, we had quite a good R-squared compared to a lot of these studies. And again, we have the same fixed site continuous, short-term mobile, and short-term stationary. So this is more like, this column is more like us, where it was a mobile campaign, but they stopped for some length of time. And we see similar results for black carbon. So we had quite good model performances compared to many of the other studies, with the exception of a couple of some of the fixed site continuous. But if you look at this based on the number of sites we visited, the number of visits per site, or the visit duration, then we are pretty clearly different. You know, we have quite a few sites compared to most studies, except for the purely mobile, some of the purely mobile studies. And the fixed site continuous studies, it's not really realistic for them to visit that many sites. And many of them are either there just one time, or maybe they come back a couple of times. But we, you know, went back on average 27 times, but we didn't stay very long compared to the short-term stationary. We stayed much shorter time, and of course much shorter than the fixed site continuous. So yeah, that's what we learned from that study. And what I wanted to, you know, what we don't know the answer to is, do we really need to stop? But we have a lot of mobile data that we're now working on integrating into our modeling to look at the on-road data and ask questions about whether we need to park. One of the reasons why we decided to park is we felt like then it's more like what somebody would breathe at their residence if you're actually pulling over off the road as opposed to following a diesel truck or a school bus or something. Another thing, and this is what this figure points out, these are various sensitivity analyses that Magali did, looking at different ways of coming up with the annual averages. For instance, instead of using the median, she used the mean. Here's where she trimmed more. But this one, the Windsorized mean, is the one I really wanted to focus on. So, you know, Windsorizing is where you, instead of trimming the most extreme observations, you set it to the level where you're Windsorizing. So like the next lowest concentration. And what pops out in this figure is the dramatically higher ultrafine particle predictions around the airport in Seattle. And I think that makes actually a lot of sense, because what we know, and you know, some of this important work has come out of your institution and Southern California. We know that airplanes, as they're landing, they send a lot of ultrafine particles down to Earth, and they bathe the area underneath of them with ultrafine particles. And they're actually also quite small, which we haven't looked at yet, but we should be able to pick up in our data. But, you know, unlike a busy road, airplanes aren't overhead all the time. They have a regular but uneven landing schedule. And so my suspicion is that, you know, in our 27 visits, we're not picking up as many of the landings. And if you Windsorize so you don't throw out that highest observation, it's probably a meaningful high observation, and you use it instead, we're picking up a higher exposure around the airport. So I think there's some interesting work to be done, and really thinking about how to use data given the limited sampling we're able to do. And so I went through a lot of this pretty fast, but let me go over the takeaways and then I'd love to hear your questions. So what I think we learned from mobile monitoring study design for epidemiology is the study design actually matters a lot. And most of the published studies are not using an appropriate design, but they're using those estimates in epi studies. And the year-round balanced design performs best. It doesn't seem to matter too much if you have some restriction in hours of the day, which is logistically, I think, one of the most challenging things about doing a mobile campaign. And we don't know yet whether we can have some sort of a reduced balanced design, maybe, fewer weeks of the year, but more balanced across the year and so on, whether that would work. An important takeaway is traditional model assessment doesn't reveal the design flaws. And I think that's an important thing for us to think about as statisticians, because we typically rely on the observations as some measure of the truth. And when you've got a biased design, that's not true. And we're speculating that unbalanced designs may result in differential exposure misclassification. And I say this because the biases can vary by site, and those biases are associated with site-specific time of day patterns. So what I put up here was smooth plots across our 69 sites of by hour a day and season, what the concentrations are. And you can see that if you restrict sampling to very specific hours of the day, you're not necessarily going to get the right annual average, and that's going to vary by site. And I think that's a really important point that is probably actually not fixable. And it's got to do with how you sample. And once you sample, I'm not sure that it's fixable. From our Seattle mobile monitoring studies, we found that our prediction model performance was superior to other mobile monitoring studies. And this suggested that you don't have to stay very long at sites, but you have to go back a lot, sample often. And I think, but we'll answer this question better in the future, that more sites are better if you want to capture the kind of complexity of the exposure surface. You want more than the kind of typical like 50 or whatever sites that exposure assessors will recommend. Stop locations should be representative of the study cohort in order to have spatial compatibility for measurement error corrections. And I didn't talk about this, but the logistics of a mobile monitoring study are actually quite complex. You have to plan for all kinds of things. Maintenance and makeup routes and drivers getting sick and drivers being safe out on the road late at night and data quality checks and good database management. So there's a lot actually behind a good mobile monitoring study. And finally, this is my last slide. In terms of mobile monitoring for epidemiology, I think it's feasible for measuring ultrafines and other less commonly measured traffic-related air pollutants. But it's a lot of driving. We had over 1,600 hours logged in our mobile monitoring campaign. However, the duration, and that's for any one site, can be very short. And as I said, we're looking at the on-road data there. We're talking about seconds, not minutes. And that will also increase our spatial coverage. But in general, mobile monitoring allows us to get increased spatial coverage. And also you can use more high quality instruments because you only need one platform and to measure multiple pollutants at the same time, and even to put duplicate instruments in the platform, which is important for quality control. But there's some things that are really important that we don't yet understand, like, can we use on-road samples? Should we have to park? Are there ways to reduce the effort, like fewer stops or shorter time periods? And I'm leery of the last one, but is there any way to correct predictions from the common design so that they're not biased? So that is the end of my talk. I want to thank you very much. And I'm going to stop sharing my screen so I can see everybody, and I'd be happy to answer your questions.
Well, thanks very much, Lianne, for something that hits right close, very close to home in terms of the designs of our own air pollution studies. I'm going to open it up to questions, but first I just wanted to pick up on your comment about the 1,680 hours. Do you have any sense of what's the relative cost of mobile monitoring versus the various fixed monitoring stations that we more traditionally use?
Well, actually, I have a project that hopefully will get at that question better in the future. But I can say, and this didn't fund everything, but because our ACT AP study was co-funded by National Institute of Aging, and they've got a lot of extra money right now to study Alzheimer's disease, we were able to fund this mobile monitoring study with an administrative supplement of $250,000. Now, so that gives you a sense for driving in a year. That covered the cost of some instruments. It covered the cost of the driver. It didn't cover all the costs of the planning. It didn't cover all the cost of the database management after the fact. We just finalized our database actually last week. I mean, we had it, but we hadn't cleaned up all the little details and files and so on. Even with a really high quality database, it was amazing to me how long it took to get all the details right. So that gives you a sense. I think you probably, with experience, could do it for 250,000, but maybe I'm a little bit naive in terms of that.
Yeah, well, we've typically deployed fixed site monitors at kids' homes, and that itself is not cheap.
Yeah.
That's the reason for my question. I have other questions, but let's open it up to others. Anybody have questions for Lianne?
I'll go ahead and ask a question. So Lianne, this is a really great presentation. Thank you. I've heard of some people or some groups having what I would consider almost a convenient sample of sort of mobile monitoring, like maybe putting a monitor on like a light rail or something like that. Given what you've found about how important the design is, do these kind of data from this kind of convenience mobile monitoring, do you think they play a role, or do you think it'd be too challenging to incorporate that kind of data?
Well, I mean, there's lots of reasons to do exposure assessment, right? And I certainly don't want to comment on all the other reasons because there could be value added in them. But for epidemiology, where your interest is in estimating a good long-term average, I don't recommend it. And, I think that's an awareness that's not out there in the literature. I think people think, oh, we've got all this great data, let's use it for this purpose. And I think we as statisticians maybe need to help disabuse people of that idea.
Maybe can I ask a follow-up question? You mentioned that, in your simulation study, you had the true exposure surface, you were able to validate your models, and I didn't quite fully grasp, but you were mentioning how, the usual ways we validate our models or assess our models seem to not work. Can you maybe recap that and what the takeaway is for how we should be assessing our models?
Yeah. Well, the thing is in practice, I don't think you can do anything else, right? So when you assess the model, you compare predictions against observations, and you treat the observations as the truth. They're a noisy version of the truth, but there's still a version of the truth. You don't have the gold standard, right? I mean, we had the gold standard because we had a simulation study and we had the data, and it wasn't necessarily the true annual average at those sites. It was based on all the measurements. We called that the truth, but of course, even at regulatory monitoring sites, they don't sample every hour all the time. There's missing data for lots of reasons. So, that setting that aside, it was our truth in our simulation study. But in practice, I don't think you can do anything but assess your model performance against observations. So I think that recognizing that when you've got a biased design, that your model performance statistics aren't telling you what you think they're telling you. I think that's an important recognition. I'm not sure where to take it next. I'd love to hear if you all in the audience have other ideas on that. But the observations themselves are biased. So that's, that when you're comparing against something that's biased, it's not surprising that it's misleading.
Well, Frank's got his hand up.
Okay, well, yeah, it was a very nice talk. I think it's been recognized, and maybe Rima and others could comment on this, that many models made data, that underestimate highs and overestimate lows, typically. And so you end up with this potential bias, inflation or whatever you're talking about. I think that's pretty common. And maybe that's not what you're talking about, but I think it might be relevant. But the second
can I follow up on that before
Sure.
you? Yeah, so I mean, when you do prediction, you're going to get less variability than the data, right? Because the prediction doesn't capture everything, and so typically the predictions are less variable in the data. Yeah, so you're going to get, on average, the highs are lower and the lows are higher. But what I'm talking about here is something, sort of systematic that has to do with how you collected your data. And is above and beyond the fact that you get, that by its very nature, predictions are less variable than the observations.
Okay. And the second question I had is about, you started out talking about traffic-related pollutants, and the EC, the black carbon and the ultrafine particles. Really, you're talking now about the airport and trains and port. So you're not really estimating traffic-related pollutants per se. So if you could combine several of the measurements, do you think you could get at something that would be more directly related to traffic, then that would not necessarily be, have contributions from the airport or from the port or from the train switch yards?
Yeah, I mean, so you make a good point. I mean, our surface captured variability, both near roads, which I didn't focus on as much as those other things. But we do have multiple pollutants on our platform. And so, one of the things that we will be doing as we move forward is thinking about those multiple pollutants. And I'd love to hear ideas from you all about even how to distill those. Like, do you distill them at the measurement level, or the visit level, or the site level? Not so clear to me how we're going to distill those multi-pollutant vectors and for modeling. We want them to be annual averages, but how we're going to approach that, I'm not exactly sure yet. But I do think that we'll be able to sort out some of these things, what's really road related exposure versus airport related exposure, which actually I think is pretty important. As an example, I think we'll be able to do that with our data.
I think my remaining question was very closely related to Frank's second one, because I was interested in that plot you showed of the black carbon as a surrogate for ultrafines, highlighting the contributions of rails and ports.
Mm-hmm.
Was that picture based on your regression residuals?
Yeah.
And if so, I thought you had as covariates things like distance from those sites in the model. So why do they pop up then?
Well, so I think that the picture was based on the correlation between the two predictions. And so the residuals were, so the least squares fit was, sort of given that and I can show it again if you want me to. Let's see, given that you want to use black carbon as a surrogate for ultrafines is what the question was really focused on. So we have actually the predictions for black carbon versus the predictions for ultrafines, and both actually these were, I think, the raw estimates, and these are the predictions at the cohort locations. And then in the next slide, again, plotting the estimates at the various locations. And then here are predictions at grid locations. So, because it's a little easier to really see that for the grid locations. And so and the biggest residuals from this regression, are the ones that are circled in the black dots. And so you're seeing, the high stuff is mostly around the airport, but not completely. There's a few other locations, and the lower stuff is more downtown. And I think these are probably also highways to some degree as well, or not highways, but not the main highways, because they would be marked, but there's some other main roads in that area.
I've got a question.
Yeah.
Are there indoor sources for the ultrafines?
Maybe there's somebody on this call that knows that better than I do. I bet, I guess I don't know the answer to that.
Yes, if I may, Lianne. Hi, it's Rima Haver. Yes,
Hi.
there's quite a few indoor sources of ultrafines, from cooking to, burning incense, even, or candles, or anything you burn, or sometimes a little bit of secondary formation under certain chemistry.
Thanks.
Do they dominate the outdoor exposures, or, because most people spend their time, most of their time indoors.
Yeah, and I don't know as well as maybe Rima does about penetration of ultrafines. My guess is they don't penetrate anywhere near as well as PM 2.5 does, because they probably stick on the way into the building filter or coagulate.
Yeah, that's true. They're not as efficient as PM 2.5. But I think, in terms of contributing to total personal exposure, I'd imagine indoor sources are important in that sense. But then, of course, they are probably not as toxic as some of the outdoor sources of ultrafines.
And they're also not regulated in the same way. So a lot of our focus in air pollution studies is on ambient air pollution, because that's what's being regulated.
Remind me, when you say you use partial least squares, remind me what you're doing there.
So partial least squares is a dimension reduction approach, which uses but it's based on maximizing the correlation as opposed to maximizing the variability. So principal component analysis, we would take our geocovariates and maximize the variability to reduce the dimension. Whereas to reduce the dimension of our geocovariates, we're looking for the correlation of the geocovariates with our outcome in our model, which is log NOx. So it's a different dimension reduction approach that maximizes correlation as opposed to variability just within the covariate set.
So just to be clear, that's the correlation with the gold standard measurement?
No, it actually, so we would have done that. No, we wouldn't. In the simulation study, we would have derived those PLS components with each data set, right? Because that's the data you have to develop your prediction model, is your observations, your measurements. So, right, I mean, for comparison, it would have been the gold standard, right? But in any one campaign, long-term or short-term, it would have been the data we had, which is 69 annual averages at 69 sites obtained from however many measurements, either 28 for the short-term campaigns or however many it was for the various long-term campaigns.
Well, any other questions for Lianne?
So Lianne, thanks for a great talk. So you, as Duncan mentioned, you've done a lot of work on the Clean Air Scientific Advisory Committee, and I was just, and you just mentioned that, those are based on ambient kind of measurements for setting standards. So I was just kind of curious as to whether you'd seen a move towards using these kinds of models in any way to help assess population risks in the workup to standard setting
Well,
exercises.
you know, people who have ultrafine pollution surfaces, which prior to ours are mostly based on mobile campaigns that have some version of convenience sampling, are using those to estimate health effects. And so there starting to be more and more papers on that. And EPA, you know, in its PM assessment that it did under the Trump administration, you know, they had a whole section on ultrafine particles, but most of the evidence that they based it on was not based on long-term epi cohort studies. So that's one of the things that we're really hoping that we can contribute to. But I would say there's not a lot of literature out there and yet, but I think it's coming, and people aren't aware enough of the design. So, but we have a preprint of our paper up, and if anybody wants it, I don't know how handy I can put it in the chat. Maybe.
Is that the same as the link that you sent to me?
Oh, yeah, I think, didn't I
Okay,
send you? Did
Yeah, I put the link to that preprint in the announcement for the seminar.
Okay, yeah, Med Archive, yeah.
You'll be able to find it there.
Yeah, it just went up like last week or something, so it's quite new. So.
Well, thanks again for a wonderful talk, Lianne. And we've long been following your work, and we'll do so long into the future, I'm sure.
Well, it's a pleasure to join you all and to see a lot of familiar faces who I haven't seen in a long time. I really am, yeah, happy.
Well, I wish we could have gotten you down in person and then spent the whole day picking your brains. But I know you have to go teach shortly, so.
Yeah.
What is your class that you teach, by the way?
I teach a thesis proposal preparation class. So they write a proposal. My goal is mostly to keep them on track and to give them feedback and to help them understand how to do it. The fun thing at the end, that's what I do spring quarter. The fun thing at the end of the quarter is we do a simulated NIH peer review. So they learn a lot from that process.
Excellent. That's really worth doing.
Yeah.
Okay, well, thank you again. Let's have a round of applause.
Thank you very much.
A round of applause for Lianne. And thank you again.
All right.
Good to see you.
Yep. Good to
Bye all.
see you. Bye.